Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to be talking about the fundamental theorem of calculus. So there are going to be two parts to the fundamental theorem of calculus, and the first part is going to talk about the derivatives of integrals, and then the second part is going to talk more about like evaluating them. Don't worry, we'll get into it. So the first thing to note is that the fundamental theorem of calculus deals with functions that are in this format. So we'd have g of x is equal to x a of f of t dt. Basically, we could see now that the integral is no longer what we know it as. It was this is how we saw it before, but now we could see that these upper bounds are no longer both scalar values, or they're just like defined values. This one up here is now a variable that gets passed in as the input of our function. So this is one important thing to notice, that the integral is a function. And from that, we can kind of see that the upper bound is a variable. If we remember, this right here would tell us that, okay, well, it is the area under a curve. Let's say we have this curve that we'll call f of x, and then here is a, here is b, right? And then this integral right here basically tells us, okay, well, what is the area under this curve? And the integral will compute this area right here. However, if we look at this function now, what this is telling us is this. So let's say that we have the same function y equals f of x right here, and now instead of having this definite b value that we had over here, let's just say that this b value now is the end of our interval. And so now our upper bound is going to be x. And let's say x is somewhere here. So then what our function is going to do is it's going to calculate the area under the curve up to this x, right? And now if we move x over anywhere, let's say x increases all of a sudden, and now we need to calculate the function at this new x value, well, now the integral is going to return all of this area, right? So that's basically what this is. You tell the integral from where and to where, and it will compute the area under the function up to that point. So moving on to the fundamental theorem of calculus part 1, we say that if a function f is defined and is continuous on a to b, then the function g is defined by this, right? So here is our function g, and it has an input parameter of x that is the upper bound of this integral right here. And we can notice that the function f does not depend on the value of x, right? So then we can go on to say that g is continuous also on this closed interval, and it's actually differentiable on that open interval too. And the important part to note here of this theorem is this end right here. So that g prime of x is equal to f of x. We can think about it essentially, if we were going to take the derivative of this side, right, and then we were going to apply the derivative to here, technically these two symbols are kind of like canceling each other out, and you're just going to be left with f of x. Now we're going to go on to do a few examples so you guys can grasp this material a little better. So let's look at our first example right here, and it says to find d over dx of g of x, and it's equal to this function right here. Right? So now using what we've learned, we can easily solve this problem actually, right? Over here, I've pointed out that g prime of x is equal to f of x. So according to the fundamental theorem of calculus, if we were to find d over dx of gx, which is equivalent to g prime of x, well, that's just going to be equivalent to us plugging in this x value into our function of t, right? And the function of t is this one right here. So this is the function. So all we got to do is plug in this x value into here, and we're going to get the derivative. So now moving on to a slightly more complex example, we're asked to find the derivative of this function, and its input parameter is now x to the power of 4. So again, according to the fundamental theorem of calculus, g prime is equal to f of x. However, we can notice that it's g prime of only x, right? But here we have x to the power of 4, right? So g prime of x to the power of 4, well, we know that this right here is going to be chain rule, right? So it's like saying d over dx of g of x to the 4, right? This right here is going to be chain rule, and it's actually equal to g prime of x to the 4 times 4x cubed. And again, I'm going to link a card to the video where I talk about chain rule for derivatives. But this is it right here. This is what we're going to need to apply, right? And now we know what this is here. We know what this is, and it's we just have to use the fundamental theorem of calculus and basically plug x4 into here. Now we're going to simplify this. The first term is going to be secant of x to the 4 times 4x cubed. And there you go. There is our derivative, and we've solved it. So it's just this little extra step of recognizing that it's going to be chain rule, and we're just going to have to multiply by the derivative of the inner function. So now moving on to the fundamental theorem of calculus 2. As I mentioned, this is now going to deal with evaluating the integral. So we say that if f is a continuous function on this interval, right, then the integral evaluated is going to equal to capital F of b minus capital F of a. And we've seen this capital F before, and I've mentioned it here as well. Capital F is just the antiderivative of f. So if you haven't seen my video on antiderivatives yet, make sure to check it out. I'm going to link a card to it. But essentially, an antiderivative is the function that we would have had before we differentiated it. So again, we're going to go through two examples here, just quickly show you how we can apply this. So this first problem is quite simple. It's just asking us to evaluate this integral right here, right? So using the fundamental theorem of calculus 2, we could say that this integral right here, evaluated from 1 to 3 of e to the x dx, is equal to f at 3 minus f at 1. And now all we have to do is compute capital F, right? Well, capital F of e to the x is just e to the x plus c. However, for definite integrals, we ignore this c. So generally, the notation that we use is we're just going to write the antiderivative, which in this case is e to the x. We're going to write e to the x, and then we're going to put this bar and then 3, 1, meaning evaluated at 3 and 1. So this is going to be, the top one is going to be the first term, and the lower one is going to be the second term that we're going to plug into our antiderivative. So this will evaluate to e to the 3 minus e to the 1, or if you want to simplify that, it'll just be this. So there you go. There is the answer to this question up here. Here is another question, and we've encountered this a lot in this series already. For probably the last couple of lessons, we've been using this as an example. So I'm going to go over it now, just so you can kind of see how everything links together. So it's asking us to find the area under the curve y equals x squared from x equals 0 to x equals 1. And this is the perfect time to use an integral, because we know that the integral corresponds to the area under a curve, right? So how are we going to set this up? Well, we're going to take the integral, and these are clearly our bounds. So the lower bound is going to go on the bottom, the upper bound is going to go on the top, and next we need the function that we're going to integrate. So here it is, and all we're going to write is dx. And now this is in the form of something that we know how to solve already. So using the fundamental theorem of calculus, again, this is equal to f at 1 minus f at 0. And if we want to compute the antiderivative of what x squared is, right, it's going to equal to x cubed over 3. And again, all we do is we're going to be adding 1 to the power, so it'll be xn plus 1 over n plus 1. If you want, go over my antiderivatives video. I'm going to link it again. So I forgot to mention that f will have this plus c here. However, like I mentioned before, we are going to exclude it. So it's just going to be x cubed over 3 evaluated at 1 and 0. And I'm just going to go ahead and plug these two bounds in. So we're going to get 1 cubed over 3 minus 0 cubed over 3. So it's going to equal to 1/3 minus 0, and it's equal to 1/3. And now you can compare this answer to the rest of the answers that we've been getting in the series. And as you can see, it's always going to equal to 1/3. However, this method is so much simpler to computing versus having to do, like, for example, like computing it through sigma notation, or having to do like this huge like computation. This method is a lot easier, and we basically use the fundamental theorem of calculus from now onwards to compute and evaluate these integrals. So that's it for the fundamental theorem of calculus. Hopefully you enjoyed the video. If it's helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. And yeah, I will catch you guys in another video.